practice problems. So first we're going to look at practice problems relating to norms. And so we have this matrix, and we want to compute the one norm of it. So as I mentioned, we start with an upper bound, and we look for a vector so that A times that vector has that upper bound. So remember, the upper bound we saw for the one norm was the absolute column sum. So that's where this number comes from. So the sum of this is 3. The sum of this, absolute values, is 4. Sum of this is 3. So 4 is the largest value. So that's where this upper bound comes from. And we see that if we use this vector, when we multiply this vector times this matrix, we get this column. And so this column has norm 4, even though x1 has norm 1. So again, the absolute sum of this is 1, and so we have the relationship that we need. So this is what we have for the one norm for that matrix. For the infinity norm, again, we look at row sums. So absolute, this has row sum 3, absolute row sum 3, row sum 4. So we would use this. So this has the maximum row sum, and so our x has all the same signs as that row. In this case, they're all positive. When I multiply this matrix times this column, I get this vector, and I can see the maximum element in that indeed is 4. So it works for this. Now for the 2 norm, I'm going to start off with a different matrix, and that's because in general for the 2 norm, when we're working with singular values don't come out very neat generally. Okay, so here we start with an upper bound. It's like, where does this come from? This is actually the largest singular value of this matrix. So you might not have just looked at this matrix and said, oh yeah, it's got to be 10. No, you compute some singular values, and that's where you get it. And there's a lot of effort in computing the singular values. So the norm, a vector that has norm 1 is this vector. And so it turns out if we multiply this matrix times this vector, we get this. So, and that has 2 norm equal 10. So this is the singular vector associated with this matrix. This matrix is actually contrived to give us fairly simple numbers to work with. Generally speaking, when you work with singular values, it's much more complicated. All right, what about the Frobenius norm? So here's the matrix that we start off with. We take A adjoint times that, and we get this. The trace is 16. And so the Frobenius norm is the square root of that. And so that one's actually very straightforward. We don't have to come up with an extra vector. So this is also not an induced norm. So there is that. Now we saw that there were the p norms in general. And the p norms we saw were not NP, were NP hard to compute. Although MATLAB does have the norm function in MATLAB does allow the computation of the p norms, so we could actually use that. But in terms of finding the vector, that wouldn't be so obvious. All right. For the Helder p norms, we can actually go through and compute those. Those are fairly straightforward. Again, that's not an induced norm, but we can compute them, and so this is what happens as we vary p for this matrix. For perturbations, we've already seen that a small change can produce a big effect on the output. So given this matrix now, where these two columns are very similar to one another, except for that value, if I do a singular value decomposition on this matrix, this is my singular value decomposition. I have singular values 200 and 0.1. 200.1 and 0.1. And so the smallest additive perturbation is the matrix A, basically, with this term 0. And actually, I put the negative of this. When I multiply this all out, I get this quantity. And so this is the matrix that gives the smallest additive perturbation. Okay, so that's what it looks like. So if I take this matrix and add this matrix, so this has full rank because these two columns are actually independent. They're very close, but they are independent. So this matrix then is the smallest matrix that will make this, when I add it to this matrix, I lose rank. So given the same matrix then, the smallest multiplicative perturbation is when we choose, instead of having this 0, we now choose 1 over this value and then this 0, and that gives this matrix. So that's how we would compute the so again, we have the U, S, V adjoint. We keep those matrices the same, and we only work with the thing in the middle in terms of the perturbations for those two examples. The next example is a least squares example. So here I have this data. Again, it's noisy both in X and in Y. This data was generated from this equation where we added noise to both X and Y. So in terms of computing the least squares solution, I use this MATLAB code. So here I enter the X and Y. I go through and I do this. This gives us the ordinary least squares solution. And then I can see how that curve fit is here. I then do X bar, Y bar, which are the mean values. From that I form the B matrix, which is X minus X bar, Y minus Y bar. I do the singular value decomposition on that matrix. From that I choose the smaller vector of this, which, I mean, the vector associated with the smallest singular value. So that gives us the R values, R1 and R2. I use that to form the slope and intercept, and I go through and I see what this is, so that we can compare the data. And so here is the plot that compares the data. And so here's the plot that we get. And you can see the two lines are actually very close to one another. The slopes are almost the same, slightly different. They both go through the median point, X bar, Y bar. And so this is the example, and this shows using the total least squares and also the ordinary least squares, how the two curve fits look for a given set of data. So you can see this data is quite noisy, and so the two are doing as good as they can, considering the fact the data is quite noisy. So these are some practice problems for this presentation on norms and perturbations and least squares.